Hi. In this video, we're going to continue our discussion of vector spaces with an introduction to the null space of a matrix and how this relates to solutions of linear systems. I first want to introduce the idea of a homogeneous linear system. Homogeneous linear system is really just a fancy name for a very simple idea. It's a system of equations with a right-hand side of 0. So we can write it as ax equals 0 rather than our more general ax equals b. Clearly, we can write this type of equation for any matrix A. So any matrix can be associated with a homogeneous system, and that system is unique. There's only one way to write this equation for a given A. If we think about what a homogeneous system means geometrically, in the row picture of a system, the system is represented by a set of planes or hyperplanes. What's unique about a homogeneous system is that all those planes pass through the origin. What this means is that if all of the planes or hyperplanes pass through the origin has to be a point of intersection. It has to be a solution. We can also see this algebraically, as it's quite clear that if we put in a 0 vector here, this will solve this system. So every homogeneous system always has the solution of x equals 0. We often call this the trivial solution. But some homogeneous systems have more than simply the trivial solution. And we'll explore what that means in this lecture. The idea of a homogeneous system directly leads to the idea of a null space. The null space is simply the set of all possible solutions to the system AX equals 0. We talk about the null space of a matrix. In order to define it, we use that matrix as the coefficient matrix in a homogeneous system, and then ask what are the solutions to that system. The notation we use is often n of A or null SP of A. And we can define it as the set of vectors x such that AX equals 0. This is a conceptual definition, but doesn't really let us do anything with it. Let's dig into the idea of the null space a little more. First of all, we might note that any linear combination of two solutions or more solutions to AX equals 0 also has to be a solution. Why is this the case? Well, let's just think about it. Imagine that we have two vectors, u and v, that are from the null space. U and v are elements of the null space. What does this mean? It means a times u equals 0 and a times v equals 0. They both are solutions to the homogeneous system. Right? If we then take a linear combination of those, k times u plus l times v for some values, k, scalars k and l, and ask what is a multiplied by that linear combination, the rules of matrix algebra mean we can rewrite this as KAU plus LAV, but AU is 0 and AV is 0, so this has to be 0 as well. In other words, KU plus LV is also a solution to AX equals 0. KU plus LV is also an element of the null space. This implies that the null space is a vector space. If we take any two vectors from the null space, their linear combinations is also in the null space. It's a set that is closed with respect to scalar multiplication and vector addition, exactly how we define a vector space. So we can define a null space. We can recognize that it's a vector space, but how do we use it? How do we find it for a given matrix or characterize it for a given matrix? Well, since the null space is simply a set of solutions to a linear system, we find the null space in the same way we solve a linear system, Gaussian elimination. We can start with a augmented matrix with A and a 0 vector at the end. We will later see that this 0 vector doesn't really matter because it doesn't change throughout the process. And Gaussian elimination to a echelon form, some U, with still the 0 vector. Right? At this point, we could do a checkpoint, as we always do in Gaussian elimination. Ask, are there sort of free variables or not, and that sort of thing. If there are no free variables in this echelon form, it means there's only one solution. We know that every homogeneous system has a solution of x equals 0. So as soon as we have determined that there is only one solution, we know what it must be. It must be the solution of x equals 0. We don't even need to go through the process of back substitution to find it for a homogeneous system. We will never reach a checkpoint of there being no solution because every homogeneous system must have a solution. We can never end up with a row of all zeros except for the last column because the last column is all zeros. If there are free variables, we would want to find a general solution to describe this null space, perhaps in parametric form. And we would do that by then performing back substitution, continuing on from U and 0 to a reduced row echelon form, R and 0, and then follow the same process we've done for many examples by this point. Solve for the pivots and variables in terms of the free variables, substitute a parameter for each free variable, which can take on any value, and we would be done. Let's go through an example. Right? If we have some system AX equals 0, characterized by this matrix A, start with our augmented matrix, carry on through Gaussian elimination in our standard form. Pivot in the upper left, eliminating downwards. We actually see that the second row here is simply 2 times the first, so this first step of elimination gives us all zeros. The second row, the third row is almost exactly the same as the first. The only difference is in this middle position. So when we subtract the first row from the third, we're left with all zeros except for this one position here. We end up with we would move down to our next pivot, column of all zeros, so we just move over. Another 0 where we would like there to be a pivot, but there's a non-zero entry below, so we exchange rows. We now have our pivot in the position we would like it to be. We are actually in our echelon form now. We can do our checkpoint. We have a free variable here in position 2, and a free variable here in position 4. This is an augmented matrix, so this last column is our right-hand side. 2 free variables. We will have multiple solutions. We need to carry on the rest of the way. We scale that pivot, eliminate upwards. And because this is actually a row of all zeros except for 1, the only effect that is to zero out that one position. We then move over to our next pivot. It's already 1. We are in our reduced row echelon form with our matrix R and our right-hand side of zeros. We then can cast this back into a system of equations. The first reads x1 plus 2x2 plus 2x4, this should read, equals 0. And the second reads x3 equals 0. The last is just a 0 equals 0. Rearranging this gives us x1 is negative 2x2 minus 2x4, and x3 is 0. Substituting s for x2 and t for x4 gives us our parametric form, right, where s and t can take on any value. There's nothing different about this approach than solving systems as we have before. Right? This then would be one way of describing the null space. The null space is the set of vectors that satisfy this parametric form. Right? However, we can dig into this a little bit more, and we can find another way to write the same system. I've just rewritten that exactly the same parametric form as a column vector instead, just so that we can see things a little bit more clearly. And what we see is that every term in here consists of either a term involving s, a term involving t, a sum or a linear combination of those, or in one case a 0. Right? This suggests that we can split this apart into a component that includes the s's and a component that includes the t's. Right? So we separate all of the terms that have an s. The first has negative 2s, the second has a s, the third and fourth have no s, so we put in zeros. The piece that has a t, the first has negative 2t, 0, 0, and t for the last piece. At this point, we have every term is something times s, because of course 0 can be thought of as 0 times s. And in the second vector, everything something times t, since 0 is the same as 0 times t, which means we can factor out an s from the first, giving us s times a vector, negative 2, 1, 0, 0, plus t times a vector, negative 2, 0, 0, 1. What we've done here is that we've rewritten our general solution as a set of all possible linear combinations of vectors. We have some vector given here, another vector here, and the general solution is the set of all possible linear combinations where s and t can be any real number. Right? It makes sense that we can write the general solution in this way because we've already demonstrated that the null space is a vector space. A vector space is a set of all possible linear combinations of vectors, and thus it makes sense that we were able to write our general solution in this way. Because of the connections to a vector space and the meaning of the null space, this actually turns out to be a much cleaner, more elegant way of writing a general solution for at least a homogeneous linear system. Okay. These were, we found that result simply by finding our general solution in the normal way and then factoring out our parameters to find this linear combination form. We can also find this representation of a general solution more directly by solving for something that we call the special solutions to a homogeneous system. When a homogeneous system has more than just the trivial solution, it must have an infinite number but we can characterize a small number of what we term special solutions by setting the free variables to a very specific set of values. A special solution has exactly one free variable set equal to 1 and all others set equal to 0. Because each special solution sets one free variable equal to 1, we can do this for as many times as there are free variables. There are as many special solutions as there are free variables. And these special solutions give us a more direct way of getting that result that we just demonstrated by factoring the general solution. Right? Let's look at this same problem again in this perspective of special solutions. We've already done Gaussian elimination on this system, and so I'll skip those steps and simply show that we can move from our augmented form A0 to our reduced row echelon form, and this can be cast into the language of system of equations, as we already did. And I have that same typo here. We have two free variables, x2 equals x4, which means we have two special solutions. Rather than taking this and expressing it in terms of parameters, we're going to simply plug in our two choices for our free variables. In the first case, we set x2 equals 1 and x4 equal to 0. And in the second case, we do the opposite. We set x2 equals 0 and x4 equal to 1. In the first case, if x2 equals 1 and x4 equals 0, then we would have x1 plus 2 plus 0 equals 0. So x1 must equal -2, and x3, well, x3 is always 0. That gives us a special solution of -2, 1, 0, 0. Our other special solution, x2 equals 0 and x4 equals 1, x1 plus 0 plus 2 equals 2. Again, x1 has to equal -2, and again, x3 equals 0. This gives us another special solution of -2, 0, 0, 1. These are exactly the same vectors we saw when we factored out the parameters from the parametric solution. If we have these special solutions, we can directly write the general solution as the set of linear combinations of these. Some parameter s multiplied by the first plus some parameter t multiplied by the second, where s and t can take on more values. It turns out that we can even find these special solutions more directly because they are hiding directly inside the reduced row echelon form. This requires a little bit of a processing step, thinking about what where the values are. It's not as simple as pulling out a row or a column, but all of the information is there. Right? Here, I'm starting just with A and the reduced row echelon form of that, ignoring the last column since of the augmented form. There's no reason to carry around the right-hand sides when it's all just zeros. We notice that we have two free variables, x2 and x4, so we have two special solutions. Set those special solutions up as column vectors, and we know that one of them will have a 1 for one free variable and a 0 for the other, and the other will have a 0 and a 1 for the free variables. This is how we always set up the special solutions. The question then is, how do we fill in these pivot variable entries? Well, we can find these simply by looking at the reduced row echelon form of A. The way we do this is after setting one free variable to 1 and the others to 0, we select the corresponding column. And what I mean by that is the column that we set to 1. In this case, we set x2 to 1, and so the column we're interested in is the second column. To highlight the attention, I've grayed out the 0 row and the other free variable column, and I've placed in bold red this second column that we care about. To get these pivot entries, we simply look at this column. The entry in the first row corresponds to a pivot in the first position. That's what the pivot is. Right? And so we see that there's a 2. We negate it in the answer. We put down a -2. The second entry here is in the second row, but the pivot of this row is in the third position. That tells us that we're looking in the third position. And we take the negative of this entry. So we took the negative of 2 and we put it into the first position, the negative of 0, and we put it into the third position. For the second special solution, here it is x4 that has been set to 1. We're interested in the fourth column. So again, just to highlight attention, I've bolded that column and grayed out the rest. In the first position of this column, that corresponds to a pivot in the first position. We put a negative and move it into the corresponding position. The next has a 0 corresponding to a pivot in the third position. We put a negative and move it here, where again, because it's 0, the negative disappears. Once we've reached the reduced row echelon form, we don't even need to move into a system of equations. We don't need to do any rearrangement of the system. Our special solutions are sitting right inside this matrix. Okay. One more example to sort of highlight how we do this in maybe a more sort of general sense. Imagine that we started with a 4x5 matrix, and after performing Gaussian elimination, we had a reduced row echelon form that looked like this. We have pivots, pivots, and pivots in 3 positions. Once again, this means we have 2 free variables. Our free variables are x3 and x5. We have 2 special solutions to match 2 free variables. For the first one, we set x3 equals 1 and x5 equals 0. x3 is 1 and x5 is 0. Set up our kind of vector for our special solution here. It's x3 that has our entry of 1, so we go to the third position and we walk down this column. We negate the entries, -a, -b, and -0, and we put them into the appropriate spots. The first row has a pivot in the first position, so our -a goes here. Our second row has a pivot in the second position, so our -b goes in the second position. The 0 has a pivot in the fourth position, and so the 0 goes here. 0 rows are ignored because there's no pivots. There's nowhere to decide where to put it. For our second special solution, x3 equals 0, x5 equals 1. x3, 0, x5, 1. It's x5 that is our non-zero free variable. So this is the column we choose. We negate all of the entries, C, D, and E, and put them in the appropriate place. C, negative C goes in the first position because it matches up with the pivot in this position, negative C. Negative D is in the row where the pivot is in the second position, so we put the negative D. Negative E is in the row with a pivot in 4, so we put a negative E. It's as simple as this, simply reading off the special solutions from a reduced row echelon form. Okay. Now that we've discussed the idea of a null space and how we can find the null space by finding special solutions and then taking all linear combinations, now let's think about what null spaces might look like, what they might represent in some of the simple dimensional cases. In the case, for the two-dimensional case, the null space, in order to have to exist in 2D, has to have the matrices have to have two columns, right? There has to be two variables. And so if we have a case where we have an M by 2 matrix and all of the rows are scalar multiples of each other, as in this example, then when we move to a reduced row echelon form, we'll have one pivot and one free variable. That means we'll end up with one special solution. Our null space will be all linear combinations of that one vector. That's a line that passes through the origin. If there are at least two rows that are not scalar multiples of each other in the two-dimensional case, that is when we have two columns, then we will end up with no free variables. This is an example here. Two of the rows are in fact scalar multiples of each other, but the other one isn't. And so when we perform Gaussian elimination to a reduced echelon form, we get two pivots, no free variables. If there's no free variables, there's a unique solution, and that unique solution is the zero vector. Right? The null space is just the zero vector. These are the only two options, with one sort of kind of trivial rare exception in 2D. In 3D, we can take a similar sort of analysis, but we get more interesting results. Once again, we can start off with considering the case where we have all rows are scalar multiples of each other. Okay? In this case, when we have, as shown here, we have two rows that are all scalar multiples of each other. When we perform Gaussian elimination, we end up with a single pivot and two free variables. This will give rise to two special solutions. The set of all linear combinations of two vectors in 3 dimensions is a plane. We end up with a plane in 3 dimensions. If we don't have this, if we don't have just simply linear combinations, if the rows can be expressed as linear combinations of two of the rows, but they're not scalar multiples, right? This is the situation where we end up with one free variable. An example is shown here. The first row plus the third row equals the third row. So none of these are scalar multiples, but one of them can be written as a linear combination of the others. When we have this structure, Gaussian elimination will take us to a reduced row echelon form with two pivots, one free variable. This leads us to one special solution. The null space is a line. If we have 3 rows that can't be expressed as linear combinations of the others, this is the case where we have no free variables. The null space is just the 0 vector. Okay. That was our discussion of the simple cases of 2 and 3D where we have a little bit of more ability to visualize. We might now summarize what we've learned about the null space. The null space is the set of solutions to the homogeneous system with that coefficient matrix. It's the set of solutions to AX equals 0. The dimension of the null space, that is it a line, one-dimensional, a plane, two-dimensional, or so on, is indicated by how many free variables we have in an echelon form. The null space, and there's a bit of extra words here for some reason that should just be crossed out as. The null space can be described by a set of special solutions, one for every free variable, where we use those special solutions and take all linear combination of those to define the null space. And it's worth noting that the null space is always a subspace of Rn, where n is the number of columns in A. Always lives in the parent space equal to the dimension, same as the number of columns, and may be a subspace that's just the 0 vector, may be a subspace that's a line or a plane, and it can, in one very, very special case, include the possibility of the column space being actually the entire parent space, but this only happens in a very, very particular, for a very, very particular matrix, similar to the case for the column space, where the column space is only the 0 vector for a particular matrix. In fact, the same kind of matrix. Okay. The null space is defined based on a homogeneous system, but it turns out that all of the lessons that we learn about the null space with special solutions and how we solve for these also helps us solve non-homogeneous systems, systems that don't have a 0 for a right-hand side. For every homogeneous system, non-homogeneous system, AX equals B, where B isn't equal 0, we can always write an associated homogeneous system, simply replacing the right-hand side with 0. When we compare the solutions of these, some very, very interesting results come up. First of all, imagine that XP is any solution to this non-homogeneous system. So AXP equals B. And XN is any solution to the homogeneous system. So AXN equals 0. What happens when we add these together? Well, XP plus XN, what is A times that? Rules of matrix multiplication say this is AXP plus AXN, but AXP was B and AXN was 0. B plus 0 is, of course, B, which means XP plus N is also a solution to the non-homogeneous system. We can add any solution to the homogeneous system to a solution to the non-homogeneous system, and we still have a valid answer. We get another solution to the homogeneous system. If we only have the trivial solution, this then suggests we only have one solution to the non-homogeneous system. If we have multiple solutions to the homogeneous system, a null space that isn't just the zero vector, we can add any of those to a solution for the non-homogeneous system to get more solutions to the homogeneous system. We also can play around with a similar technique of taking two different solutions to the system AX equals B and see what that leads us to. Well, if we take two solutions of for AX equals B, XP1 and XP2, and we take the difference of these, A times XP1 minus XP2, AXP1 minus AXP2, this is just B minus B, which must be 0. This difference of XP minus XP0 must be a solution to the homogeneous system. The difference of any two solutions to the inhomogeneous system must be a solution to the homogeneous system. Right? These two things together, the fact that we know that we can add a vector from the homogeneous system to a vector from the non-homogeneous system and get another solution to the non-homogeneous system, means that we can build more solutions to the non-homogeneous system by adding in the null space. That we can take any two solutions, and when we subtract them, the solutions to the non-homogeneous case, we get something that has to be a solution to the homogeneous system from the vector from the null space, means that there are no extra vectors. There are no solutions to AX equals B that cannot be related, cannot be described by a vector from a solution for the non-homogeneous system plus a vector from the null space. Right? This result that every solution is related to every other solution by the addition of a vector from the null space. For any pair of solutions, XP1 and XP2, we can find a vector from the null space such that XP2 is XP1 plus XN. This means that we can express the general solution to AX equals B as the sum of one particular solution. We just have to find one solution to this, and all of the complexity, all of the infinite solutions that we may have for if we had free variables can be encapsulated by the general solution to the homogeneous system, AX equals 0. Let's take a little bit of a pause or a break and discuss the geometric interpretation of why this is. What does this mean that we have these relationships? Well, we know that the set of solutions to the homogeneous system, AX equals 0, that is the null space of A, is a flat geometric object, line, plane, and so on, that passes through the origin. We've also discussed how the set of solutions to AX equals B is also a flat geometric object, line, a plane, or so on, but one that generally does not pass through the origin. The previous result, that we can represent any solution to the non-homogeneous system as a single solution plus from this system plus a vector from the null space, really demonstrates that these two solution sets are simply parallel objects, that the homogeneous system and the inhomogeneous system, if they both represent lines, they represent parallel lines. If they both represent planes, they represent parallel planes. The set of solutions to AX equals B is just the null space translated away from the origin. The term we use for this type of space is an affine space rather than a vector space. A vector space has to go through the origin. An affine space doesn't. And the general solution, why is the general solution this null space plus the particular solution? Because all we need to do to find this general solution to this translated system is take the parallel system of the null space and translate it by this particular solution. The particular solution is the translation vector, or a translation vector, that we can use to achieve this. It's important to note that xp here can be any solution to ax equals b. There are many, many different ways that we can translate the null space and get us to this system ax equals b. This is true because the null space isn't a flat sheet of paper that has edges, but it's an infinite plane. And so the fact that it's infinite means that we can translate it in many different ways and it will still line up. We don't have to make the edges match, for example. Okay. So we've discussed how, in theory, we can express the general solution of ax equals b as a sum of a particular solution and a general solution to ax equals 0. We've already discussed how we find the general solution, the description of the null space. How do we find a particular solution? Well, of course, we can use Gaussian elimination on the augmented matrix, as we always have. Once we get there to our reduced row echelon form, we are going to find that everything we need is contained in that reduced row echelon. We don't ever need to go to a system of equations and solve it or make any sort of parameter choices directly. We'll be able to read all of our answers out of the reduced row echelon form. The way we're going to be able to do that is by taking a similar approach as we did for special solutions of the homogeneous system, but rather than setting all free variables except 1 equal to 1, we'll find a special particular solution by setting all of the free variables equal to 0. Let's just walk through a little bit about how we do this. So let's take this example here, where we have and I have the wrong right-hand side here, I apologize. I have it right in the augmented matrix, but this is incorrect. This should be 1, 5, 6, 4. If we have this system of a coefficient matrix A, right-hand side B, how would we find the general solution to this? Well, start with an augmented matrix, carry on Gaussian elimination. I've constructed this so that Gaussian elimination eliminates a lot of stuff quickly. We eliminate downward with our first pivot. We see that the first two columns are all sort of scalar multiples of each other, so when we do that, everything becomes zeros. For the rest, 1 minus, we subtract 2 times the first row. 1 minus 4 is negative 3. 1 minus 4 is negative 3. And 5 minus 2 is plus 3. For the next row, we're subtracting 3 times the first row. 3 minus 6 is negative 3. 3 minus 6 is negative 3. 6 minus 3 is plus 3. And for the last row, we're subtracting 1 times the first row. Negative 1 minus 2 is negative 3. Negative 1 minus 2 is negative 3. 4 minus 1 is plus 3. All the same rows after one step, which means that when we move down to our next pivot, skipping over a free variable in the second position, we'll get all 0 rows right away. And I'll scale this at the same time to give us our pivot of 1 here. We now have our echelon form that has been, we've taken our first scaling step, eliminate upwards, subtracting 2 times the second row from the first. 2 minus 1 is 0, 2 minus 2 is 0, 2 minus 2 is 0, and 1 minus negative 2 is plus 3. This is now our reduced row echelon form, 2 pivots that are zeros in their own columns, and 2 free variables in positions x2 and x4, noting that the last column is our right-hand side because we started with an augmented matrix. This is in a form R, and I'll call this last vector D just to give it something, just to give it a name. So what would we do with this? Well, we could translate this into a system of equations and try to get the general solution from there. But I want to highlight how we can do this without doing that. We have already discussed how we can find the 2 special solutions corresponding to the 2 free variable columns simply by looking at those. Free variables are in x2 and x4. So we set x2 equals 1 and x4 equals 0, and that means we're looking at x2. We look through this column, ignoring the 0 rows, negate negative 1 and 0, put the negative 1 corresponding to the first free variable, the first pivot variable, and the 0 corresponds to the free variable x3, 0. Completed our first special solution. For our next special solution to the homogeneous system, 0 for x2, 1 for x4. That means we're looking at the x4 column. Negate the values. A 0 goes in the position corresponding to x1, so a 0, and a negative 1 goes into the position corresponding to x3, a negative 1. Our second special solution. These are read off from the R block of the reduced row echelon form, the coefficient block. The last column has the pivot values for the particular solution we're interested in. Why is that? Well, because we choose our particular solution to have zeros for our free variables. And if the free variables are 0, then it doesn't matter that there's a negative 1 here because it will be multiplied by 0. It doesn't matter that there's a negative 1 here because it will be multiplied by 0. When we multiply those by 0, we then only have 1s at our pivot positions. x1 equals equals 3. x3 equals negative 1. And so in the same way, we take our right-hand side column. We don't negate these values. We just read them off directly. The first one corresponds to x1, so we put a 3. The second one corresponds to x3. We put the negative 1. And this is our particular solution. We have read off these 3 vectors, a particular solution, and 2 special solutions to the homogeneous system simply by looking at the reduced row echelon form. Once we have these, we have everything we need to simply write out our general solution. Our general solution is the set of all vectors such that x equals our particular solution plus any scalar multiple of our special solution 1 plus any scalar multiple of our second special solution. We can either write this in a compact form, defining our variables elsewhere, or integrate them together into a form like this. Our particular solution plus S times our first special solution plus T times our second special solution, where S and T can be any value. This form would allow us to actually fairly easily translate this into our more conventional form, this would have x1 as 3 minus s plus 0, so we can ignore that, and x2 equals 0 plus s, x3 equals -1 plus 0 minus t, and x4 equals t. If we want to double check to our other form, or if there's some reason you would like to have it in this form. I actually prefer, I think this structure is a more elegant way of presenting the general solution, and it captures all of the connections to the null space and so on. Before ending this video, I want to just spend a couple of minutes talking about a key idea that follows from some of the discussion that we've had. And this is the rank of a matrix. We've seen how the character of the column space and the character of the null space, that is, are they lines, are they points, are they planes, are they the entire space? These are both determined by the number of pivots. If there are fewer pivots than rows, then some right-hand sides will have no solution. That means the column space is not the entire parent space. And really, it's the number of pivots that dictates the geometry of the parent space. If we have one pivot, the column space is a line. If we have two pivots, the column space is a plane, and so on. If there are fewer pivots than columns, then we have free variables. If we have free variables, the null space is not the zero vector alone. And the number of free variables, so the difference in the number of columns and the number of pivots, dictates the geometry of the null space. Is it a point? Is it a line? Or so on. So a lot of these basic ideas about what the really character of the column space and the null space are relate to this idea of how many pivots there are. And how this relates to the number of rows and the number of columns. We already have a way of defining the number of rows and the number of columns, so we're going to add a new definition that captures the number of pivots. This is the rank. The rank of a matrix is the number of pivots in an echelon form. We use the notation generally simply of rank of A to denote what the rank is. Okay, quite a simple concept. The rank is simply the number of pivots. We're going to see as we move forward in the course that the rank is really, really important and has a lot of connections to many, many different aspects of linear algebra. But for the time being, let's sit with this simple definition. Okay. Once we have the rank, we can characterize 4 classes of linear system simply looking at how many rows we have, how many columns we have, and what is the rank. The first case is a full rank or non-singular matrix. This is a case where the rank of the matrix equals the number of rows and equals the number of columns. This can only happen if the matrix is square. And if there's a square matrix with a full set of pivots, this is a non-singular or invertible matrix. We know that in this case there is a unique solution for every possible right-hand side. We can also define the idea of a full row rank. In this case, the rank equals the number of rows, but n is larger than the number of rows. This is a matrix that is kind of short and wide. It has fewer rows than it has columns. But every row has a pivot. Every row has a pivot, so all right-hand sides have a solution. But there are more columns than there are pivots, so there are free variables. There are infinite solutions for all possible right-hand sides. Full column rank corresponds to the case where the rank equals the number of columns. Every column has a pivot. Every column has a pivot, so there's no free variables. Any solutions will be unique. But in the full column rank but not full rank case, the number of rows is greater than the number of columns. So while we have no free variables, we do have 0 rows in an echelon form. This matrix is kind of tall and thin, more rows than it has columns. Every column has a pivot, but some rows are 0. If there is a solution, it will be a unique one, but not every right-hand side has a solution. Finally, we don't really have a special name for this class of matrix. If the rank is less than both the number of rows and the number of columns, regardless of what M and N are, if they're square or rectangular or not, short and wide or tall and thin. In this case, there are both rows and columns that don't have a pivot. There are free variables, so if there's a solution, there will be an infinite number of solutions. But there are also 0 rows. Some right-hand sides will not have a solution. Okay. That concludes our discussion of the vector spaces. If we've introduced the idea of a column space and a null space, and seen how we can relate these to linear systems. In a follow-up video, we'll go through some worked examples, some more examples of finding general solutions to a homogeneous system, to finding general solutions to an inhomogeneous system, and so on. And in the next unit, in Unit 7, we're going to develop our language, our ideas around vector spaces more deeply to give us a cleaner way of discussing these ideas. Thank you, and goodbye.